responsible for stocking me with, let's say, 8 minutes to go, and I'll pass it up. Okay, so today, we'll be finishing up carbohydrates, and we may or may not get so much into amino acids. It'd be nice to do a little, because we won't be as rushed on Wednesday, but we'll be okay. So then Wednesday, you want to come with amino acid slides. And I'm going to do lipids last, because the lipids chapter is a really easy chapter. It's just going to be recognition. And so if we get pressed for time on lipids, what I've done before is I just put up the slides with blanks filled in for you, and you just have to be able to recognize what is a wax, what is a fat. That is just very much just look at a molecule and classify it. So that it's not that difficult. So we'll do that last. Don't forget Wednesday will be your exam 5 and the table will be due. And that'll be our last day. So we have, 3 lectures to go and then a test. Okay? Yes?
Final is on the following Monday, right?
Final is, yeah, is it the Monday or, I have one Monday, one Tuesday. I don't know which one you guys
It's the
are.
20th.
The 20th, is that Monday? Okay.
And it'll be here?
It'll be in here, yeah. And it's 2 hours. It is that standardized test. So we'll give you a periodic table and no calculators in 2 hours. And you can bring a large Scantron and a number 2 pencil. Is it what?
Which Scantron?
The big 50 question one that has a backside. There's 70 total questions. Ryan?
We get the carbohydrates.
You don't, but you won't need it. They don't ask you names or anything. They don't assume that you've got that memorized. Okay. The most they'll do is like show you sugar structures and say which one's the Hayworth projection, that kind of thing. Okay? People have found the carbohydrate or the biochemistry on it to be really easy. Alrighty? Okay, so let's continue on. Don't forget to stop me. Alright, last time, let's back up one slide. This is what we ended on, was taking a straight chain and converting it into a Hayworth projection. And some of you guys can just do it in your heads, and that's great. But for those of you that cannot, we talked about how you rotate the groups around the bottom carbon. So focusing on this last carbon that's chiral right here. Rotate all the groups so that the OH is at the bottom. So there I did a rotation. OH is at the bottom. Drop the thing sideways to the right. And then take that OH, loop it around here to form a 6-membered ring. Right there. By convention, the oxygen in the ring is always in the upper right-hand side. And to do anything else will be a little bit weird. And then the groups that are on the top go on the top here, and the groups that are on the bottom go on the bottom. The only one that's questionable is when you close up the OH onto the aldehyde. You generate what was the carbonyl oxygen, that C double bond O becomes an OH, and it could be up or down. So I showed here with a little squiggly that I didn't specify. In the next slide, we're going to take a look at a sugar that's cyclic where it's been specified, and you'll see how to deal with that. Okay, so here's the sugar, cyclic sugar. I think it's the one we just did. Let's see, OH down, up, down, up, down, up, down, up. Okay, that's the sugar we just did last time. So it came from D-glucose. So this sugar right here is from D-glucose. In order to name it, here's where we're going to specify if that OH, when the acetal or hemiacetal was made, if at the anomeric carbon, the OH is up or down. So the anomeric carbon is this one right there. And in this particular example, the OH has been specified as having closed in the down position. So if you're going to name this, you have to specify a couple things. First, is it alpha or is it beta? And then, was it a D or an L sugar that it came from? Then you're going to do the parent sugar name. So this particular sugar that we did was D-glucose. And so what we're going to do is D-glucose. What you're going to do is you're going to Then the last thing is ring size. Was it a 5 or 6 membered ring? So you're going to specify furanose or purinose. So in this case, it is a 6 membered ring, which is what? Purinose. So it's D-glucopyranose. So I specified the sugar, it came from D-glucose. The parent stem is gluco, and then purin tells me the ring size, the ose, I add back to that, it's carbohydrate. I am just missing alpha or beta. Is this alpha or is it beta? Alpha. Alpha D-glucopyranose. Okay. Now, the next slide, you try it. So I gave you sugar. What we're going to do is we're going to draw the Haworth projection through the beta anomer this time. Then we're going to do something a little different. We're going to put it into a chair, because sometimes you see these as chairs. And then we're going to name the thing. Okay, and we're assuming here, assume a 6-membered ring. So what is the first thing you're going to do?
The DOH on the bottom.
Put the even before that, before I started to adjust it like that, there's one thing I would do with this. Let's figure out what sugar it is. We'll do that first before we start dinking around with it. So, what kind of, is it a D sugar or an L sugar? It's an L sugar. Okay, so, look at your list of sugars that you guys have. And if you flip back, we have a whole bunch of sugars, but what do you see that's a problem? They're D sugars, right? You don't have the L sugars. But what do you know about D and L sugars? They're enantiomers, right? So what we need to do, in order to figure out which L sugar this is, we need to find what its enantiomer would look like. Name it, and then it's the L version of that. Does that make sense? Okay? We can't get this off the list directly, because what we're looking at is an enantiomer of what is on the list. So, I think first and foremost, what it would look like if it were D sugar. All right, so the mirror image is fine. It would have an OH here, right? And then it would have an OH here. And it would have an OH there. And it would have an OH here. Does that look like the mirror image of my sugar that I care about? Okay, which sugar is this? What do you get? Is it items? Yeah, G-U-L-O-S-E. You guys see that? That's what it looks like to me. G-U-L-O-S-E. Does everyone see that? Okay. So I'm looking at that, match them up. I see D. So this one must be L. Are we okay so far? So if we mess this up, we'll mess our name up. Okay? All right, so now we've got a name. Go ahead then, and you guys do the Haworth projection, and I'll do the Haworth projection, and we'll see if we match up.
You do it with D or L?
Your sugar is the L one, so do it with that one right there. We only went to the D because we needed to know its name. I just took that sugar up there, and it was an OH here and an H there. I want the OH at the bottom, and so I went like this. That. So when I do that, the OH is here. This becomes a CH2OH, and this just became an H. Okay, so I rotated counterclockwise. You want to put the OH at the bottom. When you're going to drop it to the side, you're going to have that.
So which direction is it clockwise or
Well, if I rotated this particular one, to get the OH at the bottom, I had to rotate it counterclockwise.
how do you determine like
It just depends where it is. If it's a D sugar, it would be over here, right? CH2OH there, then I'd have to go clockwise, right? Don't try to memorize counterclockwise or clockwise, just rotate it depending on where it is. It's a lot less to memorize. Okay, so that is, anybody else get that as their Hayward? Yeah, Gabe.
I was just curious, did I miss something on alpha, beta?
It says beta up there. They wanted it close to beta. And so the beta is alpha closes down, beta closes up. Okay, now the chair form is something that we have not seen. Sometimes you'll see these drawn in a chair form. And once you have the Hayward, going to a chair form is not difficult. So what you're going to do is draw yourself a chair. And then put the oxygen usually in that position. And then follow along, putting these guys in their positions up, down, axial, equatorial, wherever that falls. So this is my oxygen. Right here is my anomeric carbon. So coming around, it was up. The next OH was up. The next OH was up. The next OH was down. And the CH2OH was down. So what I did, I didn't even worry about axial equatorial. I just went up, down, up, down, as I went around the ring. Okay, everyone all right with that? All right, now let's name it. Here we go. Name the sugar. What would you call it? Okay, so beta, L, G-U-L-O, Pyranos, okay. Okay. That's something that on, what is it? I think on the exams we have to do one of those. So make sure you can go from straight chain to a Hayward, because you'll be asked to do that. All righty. Now, what I've got here is straight chain sugar, and then 2 Hayward isomers, I guess you could call them. What's the difference between the two?
The beta and alpha.
Yeah, one's alpha and one is beta. And only 1% is actually the straight chain form. And so there's an equilibrium set up between the alpha and the beta. And so they actually can interconvert. And when the alpha and beta forms interconvert, all it is your ring pops back open, and then it closes up from the other direction to form alpha, pops open, and closes from the other direction to form beta. So at equilibrium, you'll have some mixture of the two, of alpha and beta, and then a little bit of straight chain that has to exist to go from one to the other. That process of opening up and reclosing to the other form is called beta rotation. what interconverts the monomers between each other, so mutarotation. And what's interesting, we do an experiment in 420. Do you guys remember doing the polarimeter exercise with histidine? Remember that? And it was a mixture of the two enantiomers, right? Well, it wasn't histidine, it was a lie. What it really was glucose. That's why we're like, oh yeah, throw it down the drain, it was sugar water. And I just ruined everything for you, right? But it gives really good numbers, that's why we use it. And what we have to do, sometimes we forget to make up the sugar water solution ahead of time. The stockman will actually take D-glucose, put it into water, and it sits there for about 18 hours and mutarotates. And as it does, it's establishing whatever equilibrium it comes to. And as it's doing that, the numbers keep changing because they have different optical rotations. And so sometimes we forget and we make it up on the spot. And one student will get a reading, and the next student will come and take it, and the reading's different. And then the next, and it's different from the afternoon to the morning because it's sitting there mutarotating. And it takes about 18 hours for it to come to some equilibrium amount of alpha and beta. Then it's studied, and we hand it to you and tell you it's histidine. So we have to make that up about 18 hours ahead of time as this rotation, this mutarotation takes place. Now you're wondering what else I've lied about. That's really the only big lie we perpetrate on you. Okay, now, in terms of what you're going to get more of, it's not 50-50. It'd be very unlikely that it would be. You have a whole bunch of steric effects of the different groups on there, and also axial versus equatorial placement of groups. Some are going to be better energetically than others, so it won't be 50-50. It just depends. All right. Let's go ahead. I think we're going to start reactions now. Sugar reactions, you're not going to learn any new reactions. We're just going to take about 5 that we've learned before, like oxidation, reduction, and see how they apply to sugars and what they do. So the first one we will do is oxidation of sugar. Now you could, I suppose, go really wild, oxidize the sugar. And it has an aldehyde, which oxidizes really fast. You've seen that. And it has a ton of alcohols, which also we can force to oxidize. So you could go nuts and make ketones and carboxylic acids like crazy. But the oxidizing agents that they use on, this is actually a test to see if there's an open chain there. If there's an open chain, you have an aldehyde, so it's really a test for an aldehyde. They use pretty mild oxidizing agents, and I just want to give the list. These particular reagents here, toluenes, phthalenes, benedicts, they're all a little bit weird. They're all metals. They have a positive charge. And they want to gain electrons, so they become just a metal. And they're going to get it by oxidizing sugar. They're pretty mild, so they are not capable of oxidizing these right here. So this all stays the way it is. If you look at the product over here, the OHs are all still there. The only thing that's happened, circle the aldehyde, draw an arrow, going to a carboxylic acid. That's it. So they're pretty mild. They oxidize aldehydes. The aldehyde in particular, it's the aldehyde of a carbohydrate. So they actually call that an aldose. When you go to a carboxylic acid, it's an aldonic acid. They have some weird nomenclature in the carbohydrate industry. So these different reagents will cause you to form aldonic acids. And what they do to test to see if the open chain exists is they'll, for example, with toluenes, sometimes it's called the silver mirror test. And so what you do, if you have a test tube, you have your carbohydrate, you put in silver ion, an aqueous ammonia, put it in dropwise. If you have an aldehyde present, so if that straight chain exists, it will go to a carboxylic acid. That'll happen. So you shake it. If that occurs, what happens is silver And so your test tube will get this shiny coating on it. It'll coat out complete silver. And you can actually see that happen. It's called the silver mirror test. So you shake it, and if you see silver, then you know, aha, I had an aldehyde available. And it oxidized it.
So this can only happen with a straight chain and not the ring, right?
Right, because the ring does not have the aldehyde.
And when you make the acid, like does it stay straight chain from there on in?
Yes, once you do that state straight chain, you've killed it essentially. So yeah, you have to have, this is a test for the presence of that straight chain. If it's in the cyclic form, and it's locked in the cyclic form, and we'll see in a minute how to lock it in that form, and there's no more straight chain, then it will give a negative test, because there's no aldehyde. You have to have an aldehyde to make this happen. Copper, the two copper reagents tend to precipitate out a copper-colored precipitate, and I think it's cuprous oxide or something. It's like a brick red chunky stuff, if it works out. Okay, so we are just testing for the aldehyde. That brings us to this next slide. To be oxidized, the cyclic sugar has to be a heavy acetal. So let's sit here, if I can want to draw this up. We just talked about how the sugar exists not in the straight chain form predominantly. It's less than 1%. Mostly it's cyclic. So you would think that it would not oxidize, because in the cyclic form, there is no aldehyde. Doesn't matter if it's alpha or it's beta, there is no aldehyde here, and there is, here we go, no aldehyde. But what can happen is, if it's a hemiacetal, so you have your oxygen, that came from the alcohol that attacked, there's your carbonyl carbon, this thing can reverse itself. If it's a hemiacetal, it pops open, voila, your aldehyde, and immediately, wham, it goes to a carboxylic acid. It goes to an aldonic acid. It has to be able to open up. You have to have that aldehyde capability. So to open up, this OH right here has to be an OH. So put a circle around that right there. That has to be an OH. If you somehow block it with a reaction, you bind it to something else, it can't open up because it's not an OH anymore, and this thing will not oxidize. So you've got to have that anomeric carbon. It has to have an OH on it, right there. This bottom example is one that can't open. So we're going to do a reaction in just a little while. We're going to put a methyl group on there. So we're going to create what is now a full real acetal. It went from a hemi-acetal, which is the top one, to a real full acetal. So this is no longer an OH. It cannot open up. That's a red X right there. It cannot open up. If it can't open up, it's stuck like this. If it's stuck like this, there is no aldehyde. If there's no aldehyde, it can't be oxidized. So it would give a negative test. So that test is really to see if you've got that free OH or if it's stuck in something. And it could be stuck bound to another sugar. That's usually where it is. When you have several sugars stuck together, if you get a negative test, you know that that carbon and this OH, they were involved somehow in that bond because it's not free anymore. If a sugar gives you a positive test, you know there's an aldehyde, they call those reducing sugars, which just tortured me when I was learning this. A sugar that gets oxidized is called a reducing sugar. Because if it is oxidized, it is reducing something else, right? I don't know why they didn't call it an oxidizable sugar. That would have made better sense, but it is called a reducing sugar. Okay? That's our first reaction. The second reaction that we're going to learn is making what's called a glycoside. This is carbohydrate speak for an acetal. And going back to OChem for just a minute, somewhere I think you feel a lot more comfortable. If I had ketones, or not, it wouldn't matter, and I treated it with one equivalent of alcohol and H+. That's one equivalent only. I did there's an equilibrium between the two. Make this equilibrium. So this is like, it's like the sugar straight chain closing to the cyclic form. I've got my aldehyde, I've got one equivalent of alcohol at the other end, and it closes. So this is like making a cyclic sugar. It's a hemiacetal. Then if I took my hemiacetal and treated it with another equivalent of alcohol, H+, so this is my second equivalent, I could get this. This was an acetal. Okay? So a sugar by itself, when that OH reaches around and closes on the aldehyde, by itself, a sugar will make a hemiacetal. If I want to make an acetal, I've got to get another equivalent of alcohol from an outside source. So this is actually a reaction. You would have to make this happen. The sugar's not going to do it on its own. The sugar will go to this point right here, to the hemi. If I want to block that up, right there, that's my acetal carbon. I'm going to have to add ROH and H+. That's my second equivalent. Okay, that's from the outside. It's like from a bottle of ethanol or something. And I will put that second OR group on there. So now I've got a carbon. That's my acetal carbon. One OR group on it, and another OR group on it. Because the R group happens to be the big old long chain. Okay, so if you want to form a carbohydrate acetal or glycoside, you have to physically do that second reaction with some alcohol. Now, this is an acetal, and it's going to behave just like acetals that we use. We use them as protecting groups, right? So, in terms of its characteristics, it's stable in water. It can't open back up because I can only cleave it with H+, right? The way we got rid of our acetals was we added H3O+. This is an acetal, it's the same thing. So in plain water, it won't open back up, it can't. That means it can't butarotate. So it can't go alpha to beta to alpha to beta. There will be no straight chain form. Once I've done this to it, right here, there is no possibility of having a straight chain form from this guy. Okay? I can only get it back to my hemiacetal there, my normal sugar, by actually cleaving it with H3O+. Okay? Now, as far as naming them, it's going to be based on the name of the sugar. We're going to name the alkyl group we put on. So in this particular case, we put ethanol on there. So there's an ethyl group now. So it's ethyl. This sugar right here is D-mannose in its 6-membered ring form. So it's ethyl D-mannopyranoside. And the oside means that it's a glycoside.
Did you have to specify alpha beta?
We should actually. Yeah, we should specify. What would this be?
Beta.
Yeah, beta. So ethyl beta D mannopyranoside. Where we're going to see these when we look at disaccharides, we're going to see these glycosides formed when we attach one sugar to another. The anomeric carbon of one sugar is going to be stuck to the alcohol of another sugar. We're actually going to get that second alcohol from another sugar. And you guys will recognize that linkage when we get there. Okay, here's a crazy looking reaction. This is making ethers. I have got a lot of OHs on there. In this particular sugar, it's chair form this time. It's been closed up, so it's gone to a hemiacetal. If you take a look right there, they took that OH and converted it to an acetal with methanol. So this has been treated with methanol. And right here is a glycoside. Okay, so this is a glycoside. But then I've got all those other OHs that I can do things to. What I'm going to do with them is make them ethers. So to do that, it's a pretty straightforward reaction. You treat them with base first, you make an O minus. And then you treat them, the typical reagent, it's a methylating reagent. It's dimethyl sulfate. And it's a great way of adding a methyl group to a nucleophile. Now, you can tell me why I'm using that one. I want to add, so here I have my sugar. I have no minus in my sugar, and I am doing this. Right there, and it does this. Why am I doing that and not, for example, that? It's a what? It's a great leading group. This leading group right here is spectacular. And so it's a way of adding a methyl group with a really, really good leading group, so it'll work really well. So you put an OH, it deprotonates one of those alcohols. They show that particular one. It doesn't necessarily have to be that one first, it's just one of them. It gets methylated. Then we have this guy right there. Okay? Now, it looks like we have two completely similar OCH3s on there. We've got one here that we put on earlier, and then this one. But they're different. This one here, at the anomeric carbon, is part of an acetal. So this link right here that I'm circling, that is an acetal. This thing is a plain, boring, run-of-the-mill ether. Okay, super unreactive. It's just an ether. So then we do this again, and again, and again. And if we add enough, which typically you add more than enough, look what you do. Everybody gets methylated. So I have got here 1, 2, 3, 4 ethers and an acetal. 4 ethers, 1 acetal. Now here comes the question, why would I do this? What is the point in covering everything up with a methyl group? It looks like a really dumb thing you want to do. It's actually used to decide where sugars might be linked together. So let's say you have an unknown sugar. You know it's a disaccharide, but I don't know where the linkages are. I know they're hooked together, but I don't know where. What we're going to see with one sugar, sugar number 1, its anomeric carbon. Let's just draw a portion of it. So here's my O, here's my anomeric carbon. Its anomeric carbon will be bonded to sugar number 2. And sugar number 2 is typically just any OH. I don't know which one. Okay, just pick an OH. So what you do is you methylate everything. I methylate completely. And then I break them apart with acid. So I cleave the sugars, break them apart with acid. Sugar 1 goes this way, sugar 2 goes that way. Then I go get an NMR. And every OH on sugar 2 will have a methyl group on it. Every single one, except for this one right here. It won't be methylated. So then I can correlate it to known sugars. And I can say, aha, I know that the OH off carbon 4 is a free OH. That has to be where the linkage was, because it didn't pick up a methyl group. All the rest got methylated. So it's used to figure out where things are bonded, because one of them, where it's hooked in, will not get a methyl group. You can figure out which one that is. Okay. On your take-home, some of you guys will be given unknown sugars, and they'll talk about doing that reaction, and then they'll talk about which OH did not get an ethyl group. And that tells you where the bond was. Okay. This is showing what happens when you have the sugar, the methyls everywhere, and you treat it with H3O+. And this is not hot, strong HBr or HI. That's not what we're talking about. This is just garden variety, like 3 molar acid. Okay, no big deal. The OCH3s all along in here, this one, this one, this one, this one, they're ethers. Ethers are notoriously non-reactive. You guys have seen that. They don't do anything. This one was an acetal, right? Acetals cleave with acid. So this guy is the only one that cleaved, and it's because it is an acetal. And it knocked the acetal off, and it went right back to its heavy acetal form. And the ethers did nothing. Questions so far? Yes?
Curious, you methylated those?
Right, every single one of them, right.
Is it possible to add like a reed instead of CH3 group or something like that, and a reed R group?
Oh, I'm sure it is. I'm sure. Just typically they'll add the dimethyl sulfate is so good at what it does, and they're doing this to figure out where something's attached, so they don't typically want to add anything else. But you could. There's no reason. It's just an SN2 reaction, right? You can probably put on there anything you wanted.
Could you make it disaccharide out of that?
No, I don't think that you wouldn't do it that way. I don't think you'd use that reagent to do a disaccharide. Okay, reduction. I love reduction. Because you have all OHs and an aldehyde. And there's nothing in this molecule that could be reduced except for the aldehyde. So you didn't have to think at all for reduction. So you're going to take your aldehyde and turn it into an alcohol. Okay, and I think we're all really good at this reaction. So the alcohol is based on an aldose. They call it an alditol. It's sort of an unfortunate nomenclature. Okay, but it's an alcohol that came from an aldehyde, an alditol. Don't use that in like normal OChem, it's a sugar thing. Okay. As far as the reagents that do it, all of our standard reagents will do the trick. So this reaction is great, it's just a reduction. Okay. Now, as far as why you would want to do this, let's say you have an unknown sugar. And I take this unknown sugar. I have no idea what it is, but I'm trying to figure it out. And let's just draw. You don't need else to draw it, but you'll see why it works. This. Okay. And I am going to do this. Okay. Now pretend I didn't know this was my sugar. Okay, I have no clue what my sugar is. I'm going to reduce it. So when I reduce it, I get that. I have no clue still what it is. I just know I just reduced it. But then I go and I put it into a polarimeter. So I get the optical rotation. Tell me about this sugar. This is requiring you to reach way back to our dreaded stereochem chapter. Tell me about that sugar. It has an internal plane of symmetry, right? So what do we call those kind of compounds? Yeah, this is a meso compound. What is its optical rotation going to be? Normally, you're like, how am I supposed to know that, right? You have to go do it. A meso compound, you know. Yeah, the top and bottom are essentially mirror images of each other, right? So if the top rotates plus 10, the bottom part is rotating minus 10. What's the net rotation?
0.
0, exactly. So I pop this in, and I realize that, whoa, when I reduced whatever my unknown sugar is, its optical rotation was 0. So, go to your sugar list. Wherever it is, okay. Which sugars could this be? You don't know it's this one. All you know is its rotation is 0. Which ones could it be? Find your sugar list. I get allose. It could be allose. Right? Because that has an internal plane of symmetry if I reduced it. What else could it be? It could be, no, mannose won't work because the top and bottom aren't exactly the same. Could be iodose. Does iodose
Galactose.
work? Could be iodose. Could be galactose. Hallose, no. So it's like one of those, right? So that's tremendously helpful. I just thrown away all the others. I know it's not them. Yes? Oh, we would know that there's 6, yeah. Yeah, otherwise you'd have to consider the bulk, right? Yeah. We're assuming we know there's 6 somehow. Okay, so it narrowed it down to those. Now let's say that it had an optical rotation. Then what? I've helped myself somewhat. I know if it does rotate plane polarized light, it's not those, right? But it's certainly not as helpful. It could be any of the other 5 or whatever it is. Okay, so this is somewhat helpful in narrowing your choices down to sugars that have a plane of symmetry when you reduce them and sugars that don't. Okay, so that's just the example that we just did right there. So we reduced it, they did sodium chlorohydride, and we decided, whoops, that it could be any of those. All right. Get you up in my notes where I am. Okay. This next reaction is again helping you decide the identity of an unknown sugar. And it is making this thing called an osazone. What we're going to do is treat a sugar, we don't know which one it is, with phenylhydrazine. We have seen phenylhydrazine before. We used it in the ketone and aldehyde chapter to make imines. So we had, and let's do an aldehyde. Remember we had aldehydes or ketones, and we would treat it with H2NR and or that guy formed an imine. Right? So we're all familiar with that, I think. We've seen that a couple times. This is the same thing. Our amine that we're using, H2NR, is phenylhydrazine specifically. H2N, and then we have NH phenyl. That's phenylhydrazine. This is the part we're interested in. That's the reactant part. So when you treat a sugar with phenylhydrazine and you treat it with an excess, so this shows 3 equivalents. It has to be an excess. Something weird happens. The predictable thing does occur. And that's where your aldehyde turns into an imine. That's predictable. But what also happens is the one below the aldehyde also turns into an imine. And your book goes through a little mechanism where they show how this happens. And it's just through essentially tautomerizations and things. I'm not going to ask you guys that at all. But you just need to remember, the first one goes, that's kind of our no-brainer, we know that. The second one goes to. So you get these two. And this thing that we've created, this guy right here, is called an osazone. Let me just spell it for you, it's not on the slide. It's called an osazone. And what that does is it eliminates the chiral center at carbon 2. So what we can do is we can compare the sugar that's left. I just have 3 chiral carbons now. I compare it to sugars in my list and see which ones have the bottom 3 match up. So I first eliminate it with optical activity down to 2 groups. Then I do this, and I say, okay, who has the same bottom 3 as my sugar? Then I really narrow it down. So it just eliminates chiral carbon, is what it does. Okay, so let's see if we can use it on our list. Going on the fly here. Let's just do this one. Okay, so we narrow our sugar down to our list right there, which we did from rotation. Then we make an osazone. And we find out that the unknown sugar gives the same osazone as allose. So what could it be? Well, the first no-brainer thing was it could be allose, right? That is certainly a possibility. So could be allose. Take a look at the bottom 3 carbons though, and we'll go back to our master list. Very smart, I would have bookmarked it. The bottom 3 carbons that are chiral have the OH all on one side. So that could be certainly allose, and it could be altrose as well, right? So I know based on the osazone that this sugar is either allose or altrose. But I know it gave a rotation of 0 when we reduced it. So I know it's not altrose. It's got to be allose. Okay, so used in conjunction, those 2 tests really get you far in figuring out what your sugar is. Okay? Now, a vocabulary word for you. If you look at your list and you look at allose and altrose, they have an aldehyde. The bottom 3 are the same. They differ only in which way that second carbon, your first chiral carbon, which way the OH points. That's the only difference between those 2. There's a word that we're going to hear, epimers. And that is to describe 2 sugars that have everything the same, except for one chiral carbon is different. That's an epimer. So it's a very specific kind of stereoisomer. Okay, only one carbon differs. And it does not have to be the first one. It could be the second or the third or the fourth. Epimers. All right. We're going to scale up in complexity now to disaccharides. Disaccharides are where you have 2 monosaccharides linked together. So it's like a little sugar polymer, super tiny. And they are linked through a glycosidic bond. So we think back, we just learned that word. A glycoside was an acetal. And the linkage will occur at the anomeric carbon of one sugar. So this is forming an acetal right there. So you have one sugar with its anomeric carbon bonded to the OH, any OH on this sugar here. Any one of them is fair game. So this shows it at what, number 4? 1, 2, 3, the 4th carbon down. Could have been this one. Could have been that one. Could have been there. Could have been the other anomeric carbon too. Any OH on the second sugar, the anomeric carbon on the first sugar in a glycosidic bond. This is maltose. And the glycosidic bond, which is an acetal, is right there. So to form a glycoside, we need an alcohol. The alcohol came from the second sugar. That's our second ROH, is that second sugar. to find a way to describe this linkage. I can't say, well, I have a glucose and its anomeric carbon is bonded in a downwise fashion to C4. That's just a weird way to describe it. So what they do is they start counting with the carbons. The carbon in sugar 1, the top sugar that's involved, is C1. It is what was in a previous lifetime the aldehyde. Okay, so C1 of sugar 1, which is right there, is bonded to C4 of sugar 2. Those are the two carbons that are connected. Then I have to describe, okay, is this linkage here, with respect to the first sugar, is it alpha or is it beta? It's pointed down, right? So I know that my anomeric carbon, my glycoside, is pointed down, so it's alpha. So if I'm going to describe the linkage, what they say is it's a 1, 4 prime, meaning number 4 comes from another sugar, which always seems stupid to me, I don't know how it would monitor itself, but there it is. 1, 4 prime, alpha glycoside. Okay, so that tells you which carbons are bonded and what the direction is on the acetal. Yes? Oh, because the aldehyde carbon is right here, right? You okay with that? Okay, that's carbon number 1. So there's 1, 2, 3, 4. It's the 4th one that was down the chain. Okay, if you did a test, let's say you put maltose in a test tube, added some silver ion, silver plus, would this show up as a reducing sugar? Would you get the silver here? What do you need? What functional group do you have to get a reducing sugar? You have to have an aldehyde, right? So this thing has to be able to open up to give you an aldehyde. Well, this part right here is definitely not going to. It's stuck, right? It's a glycoside. What's going on down here? Yeah, that's free, right? You've got a free anomeric OH right there. Can pop up in here, not there, but here. There is, in this thing, a free aldehyde. And so it is a reducing sugar.
So then you have a straight chain connected to a ring.
Yeah, and you have a straight chain connected to a ring, exactly. So the only one that's new to rotating is the bottom one, alpha, beta, alpha, beta. The top one is stuck. There's another one, gentiobiose. It's 2 glucoses. So you can see a common theme on the first sugar, the top one. There's my anomeric carbon, and it's stuck. And it's bonded to the OH of that carbon right there. So if you're going to describe its linkage, is it alpha or is it beta? It's beta, okay? And it's sugar 1, right? 2, what carbon is that? Carbon 1,
6.
carbon 6. So yeah, it's a 1, 6 prime beta glycoside. Is it a reducing sugar? Yep, I've got that guy right there. It's a hemiacetal. So it is a reducing sugar. Okay, here's one we're all familiar with. Sucrose. Sucrose is glucose and fructose. So glucose is a pyranose ring, and we saw fructose last time, and it was a pyranose ring. It's one of the few that was. So, the linkage here, wow, okay. Fructose always scared me, I didn't like it very much. But, let's see, the glucose part, right there, it's my anomeric carbon, it's bonded. Not a big surprise there. So I know that it's a 1, right? Carbon 1. What in the world is going on here?
Is it carbon 2 or 5?
let's take a look. Go back to, we have to flip back to our fructose picture. It's a couple, numerous slides back. See if we can find it. Yeah, it's back before we did simple sugars. So what slide is this? I'm afraid to try to flip back to it, we'll get lost forever. Find it in your notes. And when you go down the chain, fructose has a, I'll draw it here to be more effective, has a ketone in it. So it looks like this. One, two, three, four, five. So this guy is closing up like that. Okay, that was how fructose did it, for whatever reason, that's how it does it. Okay, so if the anomeric carbon of fructose, which would be this carbon right here, I'm going to have an OH on there and a CH2OH, right? Okay, so let's find that carbon. It's not that one. It's not that one. It is
Should left. Right there, yeah.
right there. That's it right there, right? So there's the anomeric carbon, there's the OH, there's my CH2OH. So this is actually bonded through its anomeric carbon. It's two anomeric carbons stuck together on this one. So if I were going to describe the linkage, it's a 1,2' glycoside. Carbon 1 of one sugar to carbon 2 of the other. My anomeric carbons are tied up, both of them. Is it a reducing sugar? Nope, it's not. I have no free anomeric OH. I have to have an anomeric OH to be a reducing sugar. Okay. Let's see where we are. All right. Now we're going to get bigger. Polysaccharides. This is where you have multiple sugars bonded, huge polymer. You could have tens, hundreds, thousands of sugars linked together. And then there could be things also linked to the sugars that aren't sugars, different kinds of groups and molecules. But we're going to cover the two main ones. This one here is amylose, where there are 1,000 to 6,000 units tied in together. It is glucose units. Each one of these is a glucose. And it's linked by 1 and 4' linkages. And they're alpha linkages. Okay, it's found in starch. It's a component of starch. So potatoes, corn, grain, anything starchy that we're familiar with. And we digest it in our mouth. There's some, is it 309 that does that gross experiment where they chew up the cracker and spit it out, make sugar? Yeah, they do some gross experiment where they chew up saltine, I think it is, and then it hydrolyzes the starches and they spit it out and test it for sugar. You did it for Bio400 too?
Because you have amylase in your mouth.
Yeah, the spit lab, yeah. That's why I'm in this class. So, okay, so it's digested in the mouth and the stomach by enzymes. They hydrolyze the alpha linkages and it turns into sugar. Okay, so starch turns into sugar. Now, let's say you tried to eat a piece of wood. Okay, there's cellulose. Cellulose looks a lot like starch. It is glucose molecules, just like starch. It's linked 1 to 4', just like starch. It's beta linkages. And it is more rigid. It gives structural rigidity to plants. And most animals aren't able to leave the beta linkages. So it doesn't, eating grass, it doesn't do the same thing for us as eating like a potato would. And I learned, I don't know where I picked this up, that cows, horses, sheep, goats, all those things that graze out there on grass, have different bacteria and microorganisms in their digestive tract that cleave these beta linkages. And I read somewhere, fisher bugs also can cleave them. I don't know if I picked up that bit of trivia. But like us, no, not really. So because of the beta linkages. But they're pretty much the same except for the direction of the linkage. Okay, that's carbohydrates in a nutshell. If you ever take BioChem, you'll learn a lot more. All right. I won't do it to you.
I saw that look in your eye like, I really want to.
What can I do with that 2 minutes? Okay, let's go ahead and do what you really want to do today.
Take a nap.
The average was high. It was 80.